Hello students, welcome back. We just completed all the essential topics of section 1. However, there are still a couple more topics to go. One is to get us one step ahead in par with the textbook's level. The other is to take us half a step further above the textbook. Okay, here's the first task. We have to improve this a little bit. Okay, let S be a non-empty set, which we'll call the sample space. And then the elements of S is going to be called an outcome. And an element, no, excuse me, not element, the subset of S is going to be called an event. And then the probability is a set function defined for all events or all subsets. And if I use symbolic expressions, I can use this kind of expression. S is a sample space, alright, and any element of S is an outcome, great, and any subset of S is an event. So far so good. Next, here, this is what I'm talking about. Now, whenever you have a function, you have to have the domain and the target specified. Go back to everything that we did in college algebra level, trigonometry level, calculus level, and certainly in analysis. Every time you have a function is introduced like this, or at least nearly every time. Defined in a certain set here, domain, and then the target. So if I use this over here, a set function P, like this, then we don't need this. Defined for all events, this part is completely unnecessary. Let's strike it out. Why? Because this power set is a set of all subsets. So all events is covered here. The domain is the power set, so defined for all events. So you can cross it out. Furthermore, now look at this target part. Function value is going to this target, and target is the closed interval 0 to 1. So any probability should be between 0 and 1, greater than or equal to 0, and less than or equal to 1, which means this first axiom here, which I just marked in blue, is totally unnecessary. This part covers this one and also this too. Let's strike it out. Font, and then strike it out. Kind of hard to see. Let's undo that. Undo. It doesn't work. Okay, let's go back to this font. Okay, alright. Okay, so this part is unnecessary because this one already took care of that part. Next. Now this can be a bit tricky, but it turns out that this part is also unnecessary. The probability of the empty event is 0. You don't really need that as an axiom. That too is unnecessary. So this red part is unnecessary. The blue part is also unnecessary. Why this blue part is unnecessary? Because I already specified. You see, whenever you define a function, you need domain and target. And domain part took care of this, and target part took care of that. Now, why we don't need this, that's a bit tricky, but we have to come back and discuss and prove it, because that's what our textbook author does. And finally, this one is essential. So, instead of those 3 axioms we had before, we are down to just 2. The probability of the total sample space is 1, and then the addition rule. So using only these two, you should be able to prove that the probability of the empty set is 0, and also, let's see, the probability comes between 0 and 1, as a matter of fact, that's 2. And that is what our textbook author does. So, probability is always non-negative, and then probability of the entire sample space is 1, and finally the addition rule. So with these, you're asked to prove this one, and also this part you assume, so less than 1 part as well. So how do you do that? This one here, probability of the empty set is 0, is proposition 1 of our textbook. And the proof is here, but if I just show you, I don't want to reveal the answer all the way right away, so let's do it still one at a time. So alright, probability of the sample space is probability of, oh wait a minute, it's going to be easier this way. Entire sample space can be written as the sample space itself union of the empty set. And it's a disjoint union because there's no overlap. By the way, already there's nothing there, so no overlap, of course. So probability of this entire sample space is gonna be probability of this alternative expression of the same thing, and then we're gonna use this addition rule. Whenever we have disjoint union, mutually exclusive union, we can add up the probability. So probability of this S like this. Therefore, what we have, probability of this empty set is probability of this entire sample space, and actually this one, minus the same thing, and that's 0. You see, if I flip this to the other side, I have subtraction. So in the end, what did you get? The probability of the empty event turns out to be 0. What did I use? I used this axiom, and I didn't really use this axiom either, as a matter of fact. I used only this one. Okay, alright. Here our textbook author assumed probabilities are all non-negative, but here I want all is less than or equal to 1 as well, so that you have this. Okay, one part is assumed, the other not assumed, so let's prove this part. How do we do that? Let's prove the probability of anything is less than or equal to 1. Any event is less than or equal to 1. Let's try to prove that. But of course, doing directly is going to be a little bit difficult. So let's start from the disjoint union business, which is A, and then mutually exclusive union of A complement. Okay, that's the idea of the complement, right? Let me see. Yeah, here's a visualization, A and A complement, everything other than A, and vice versa. So yes, that's actually the definition of the complement. Therefore, probability of this thing, copy and paste all those. It'll work. And then we can apply this addition rule again. We have mutually exclusive union, so we're just adding up the probability. Alright, are you with me here? Now, probability of the whole space is 1. That's part of the axiom. So probability of this entire space, entire sample space, is 1. So this thing, we express it as 1. And that is equals to probability of A plus probability of A complement. Oh no. So far so good. And then that is probability of A. And then you see any probability is non-negative. So if I throw this one away and make it 0, then I'm going to end up reducing it. So, whatever the probability, I have less than or equal to 1. So, we got up to this. Probability of A plus probability of A complement is equal to 1. We get that. And at final step, if I cross this one out, or maybe I just take an extra step. So if I reduce this one down to 0, then I end up reducing it. Well, this is a bit too confusing. Let's just go back to where it was before. So if I cross out a non-negative number from being added, so I reduced it. So we got down. So the probability is less than or equal to 1. So we get this part as well. A little bit tricky, yes, and that's why I kept these out of the elementary stuffs or essential part. Our textbook author does quite decent job keeping all this axiomatic system elegant and precise, and you just saw one of those examples there. And of course, if you want precise treatment the way our textbook author did, you can look up page 56 of our textbook, but that I think was a little bit more difficult. Even though the idea is the same, it was written in a little bit more difficult way, I thought. That's why it went through this computation before. Okay, that's one of the 2 topics done, including those 2 proofs, proposition 1 of the textbook. Now, we're now on par with our textbook. Let's go now a half a step ahead. There's a bit of a problem, even with all the adjustment here. This thing is not always correct. If you have a finite sample space, no problem there. It works out great, no problem there. But for infinite sample spaces, especially for uncountable sample spaces, things will go wrong, even for such elementary cases like these. This kind of thing. The geometric area problem, even there, this kind of thing breaks down. We have to restrict the domain a little bit, as a matter of fact, because it turns out there are some sets that cannot be considered an event. In other words, there are some sets to which the probability cannot be measured. It's weird, but it happens. And it happens even for such a simple geometrical measurements like length and area and volume and things like that. It's how it happens is a little bit difficult to prove, but it turns out you can construct a certain set, and then you can create all those translation of that, which turns out to be disjoint from each other, and consequently the measures are all the same. And then taking all the union, you end up with entire sample space. Excuse me. Especially interval 0 to 1, if it is length. And then here's a problem. If those sets have probability or area or length 0. In that case, adding bunch of 0, we have to get 1. That's impossible. And then if you have strictly positive length or area or any kind of measure, probability, in that case, adding up same positive number infinitely many times and still come up with 1, again, impossible. It just doesn't work out that way. So somehow we have to improve, and one way to do that is to restrict your domain. Instead of taking entire power set, we have to go down to appropriate domain. But because we went down a little bit, which is not the same as the entire power set, this domain must satisfy its own set of axioms. This kind of example is kind of similar to like this. You see, if you have a function, a real function defined like this, then no problem. But then again, if you define a function like this, now this is going to be a problem because this expression is not always valid for entire set of real numbers. You have to restrict your domain. Oops. That's not what I wanted. Like this. Now everything makes sense because I got down to a smaller domain. When x is non-negative, then it can go to inside of the square root. Similar thing is actually happening here. Entire power set is not good. I have to go down a little bit, and we have to have appropriate domain. And any subset of S that's member of this domain is going to be called an event. And from there, we can define a probability. But then again, this domain must satisfy its own axioms, and here's one. The first, the empty set and the whole space must be part of that domain. Otherwise, you can't have this. So yes, this is necessary. Next, if a certain event is in the domain, script A, then its complement is also in there. Finally, if you have a sequence of events, A1, A2, A3, A4, A5, and so on, all in the domain script A, then its union is also in this domain script of A. So we have to have additional axioms for the domain of this set function, these three. And then of course, the set function itself must satisfy these axioms. And this one is something we already discussed, and the axiom for this domain here, it's called the condition of sigma algebra. And the reason I'm giving you this term sigma algebra is because it'll make it easier for you to look up whenever you become curious about this. All you have to do is to just type in sigma algebra to Google search or Wikipedia, and you'll be able to find out some nice information about this condition, about this domain, and the details of the definition of the probability itself. By the way, the possible domains or possible sigma algebras that satisfy these conditions includes entire power set, yes, in case of those counting that worked. And also there are some other things, but hey, look at this trivial example. If you have only the empty set and then whole space, it still satisfies all this condition. Of course, in this case, the probability is too simple, too trivial that it becomes utterly uninteresting, but at least theoretically it makes sense. Of course, most of those sigma algebras that we are interested in will be in between these two. Okay, that's how we can define the probability in really precise term. So that's where we're going to stop, and so much for the optional topic. Thank you.